Okay guys, video 3 of chapter 14, last one. We are going to be dealing with one topic, colloids. Okay, so far we've been talking about solutions, right? Solutions are fantastic, yay. Well, sometimes you don't quite have a solution, like not even close. So some solutes, when put in a solvent, don't dissolve. And they remain very large. Okay, so you take a solute, put it into a solvent, and the amount of dissolving is very, very small. Okay, you still see nice big chunks of solute floating around. Okay, an extension off this point, these particles settle out. So they will slowly but surely settle out to the bottom of the container, right, to the bottom of the solvent. These are not solutions. Okay, remember, solution is homogeneous. This would be, without being too specific, this would be considered a heterogeneous mixture. Okay, not a solution. No dissolving or very little dissolving is actually occurring. A simple example: take water and sand. Right, put a whole bunch of sand into water. All those sand particles aren't going to dissolve. They're just going to float, not float, but sink straight to the bottom and collect there. Not a solution, right? So, to quickly recap, definition of solution. Solutions are when our solute particles are molecular size, meaning they are small. Okay? That's all we're talking about. You take something like salt, put it into water, and it dissolves. Basically, that salt crystal gets broken down into teeny tiny ions. And they're just so ridiculously small you don't see them anymore. And they're all nice, homogeneous, spread evenly, uniformly throughout the solvent, and you have your solution. So we have kind of two very different ideas here. We have, hey, particles are really small, we have a solution. Particles are very large, we don't have a solution. You have a mixture. Well, what if you are in between? Okay, and that's where we get colloids. Okay, in between, we have colloids. So, I'm sure you guys can probably already fill this out. The particles are relatively big compared to molecules, right? Particles larger. I actually kind of don't like the sentence. Okay, particles larger than small molecules. Okay, but not large enough to settle out. Okay, they're not large enough to separate. I want to add one other point here. I'm going to cram it in down here. Due to gravity. Okay, ugh, that looks terrible. Oh well. Hopefully you guys can see that. If you can't, you heard it. Particles larger than small molecules, but not large enough to separate due to gravity. So these are particles that still stay suspended in the solvent, right? They don't sink. So it kind of looks like a solution with a few other varying characteristics here we're going to look at momentarily. So these molecules that make up colloids, they could be just really, really big molecules, like molar masses in the thousands, all right, or tens of thousands, all right. Molecules, guys, can get huge. They can get absolutely huge. Hydrocarbons, there you go, millions of molecules that are just gigantic. So when you start getting into molar masses of like 53,000, that's when you start getting into colloids. They just get so large, but not large enough that they actually sink. Okay, that's what we're talking about here. All right, let's go over some details of colloids. Okay, let's discuss some details of colloids. So as stated, particles are large, and they're large enough to scatter light. This is one way we can tell the difference between a solution and a colloid. Okay, colloids tend to appear, because they scatter light, they appear cloudy or opaque, meaning light doesn't go through them at all. So this whole idea of light, scattering light, if you shine light through a colloid, the light beam can be seen as it passes through. There's a name for this. It's known as the Tyndall effect. Okay, if you look at the image down here that I've got, you have here a colloid on the left and a solution on the right. Notice the solution is looks all homogeneous. Guess what? So does a colloid. Okay, colloids do look all homogeneous, all evenly spread throughout. But this one, it's pretty easy to tell, is very, very cloudy. And when you shine a beam of light through both of these substances, you can actually see the beam in a colloid, but in a solution you can't. Okay, if you the example right here, fog. Fog is a great example of a colloid. Okay, fog contains sort of liquid H2O molecules, right? Enough liquid H2O molecules, vapor, that it's actually enough to scatter the light, right? The water doesn't sink, right? Fog doesn't mean rain, right? If you're walking through fog, it's not like the water's falling down at your feet. It still stays suspended in air. All right, you can't. Scratch that. It stays suspended in air, and light shining through it like car headlights. You can actually see the beams of your car headlights. Okay, kind of neat. Smoke is another great example of a colloid. Okay, smoke stays suspended in air, but the particles are large enough they can actually scatter the light. Let's get real crazy. We can have foams, are a good example of colloids, like whipped cream. Okay, whipped cream. Which I'm not that big of a fan of, but if you look at whipped cream, it looks all nice and white even throughout, but that's a colloid. All those particles in there, the solutes are big enough, it actually causes it to be opaque, but they're not large enough that they all sink out. Milk, another example of a colloid. Okay, all the fat molecules stay suspended in the solution. Paint, great example of a colloid. Marshmallows, you have a gas and a solid, right? They, puffed up marshmallows. It's another example of a colloid. Pretty good. So all those are good examples of colloids. And one way we can tell is this whole idea of a Tyndall effect. Okay, moving on. Okay, a couple different terms we use with colloids and a lot of things. I'm going to show you guys some images here in a few moments of this. But we have what we call hydrophilic, hydrophilic colloids, which literally means they love water. You can think of it as being polar. Okay, remember water is polar, so if you have something that dissolves in water and likes water, gets along with water, it's known as hydrophilic. And that is a stark opposite to hydrophobic colloids. Which literally means water-fearing. You can think of this as being nonpolar. Okay, so we have two different types of colloids. Some of them get along with water and some of them don't. All right. One of the ways we can actually take a substance that's hydrophobic, so something like nonpolar, we can actually make it hydrophilic, or at least partly hydrophilic. It can be made to quote unquote love water by the adsorption of ions. Okay. If you think about it for a moment, ions, right, are charged particles, and water being polar is a charged molecule. So if you take something that's hydrophobic, meaning it doesn't really have a whole lot of charge, very, very nonpolar, doesn't really get along with water, you can actually add ions to the surface of it. That's adsorption. And you can kind of give it those charges, making it kind of agree and get along with and dissolve and spread out in something like water. So that's one way to take a hydrophobic substance and make it a little bit hydrophilic, make it get along with water. Some great examples of molecules like this are in a picture here I'm going to show you guys. Okay, I've got two images here. If we focus here on the image on the left, here we have a model of a molecule. This is known as sodium stearate. So here's the sodium ion. We can kind of ignore that for right now. And here's the stearate part. Notice stearate is actually made up of some oxygen atoms up here connected to a whole bunch of hydrocarbons, right? These are all carbons with hydrogens attached to them. So if you'll notice, this molecule, this entire train of atoms is all very, very nonpolar, right? Hydrocarbons, right? Just carbon and hydrogen, nonpolar. But the top right here has some oxygens in it, not symmetrical with the rest of the molecule. So we have kind of a polar end here, okay? We have oxygen, which is highly electronegative, so it's going to pull the electrons towards it, but the whole rest of the molecule is all nonpolar. So we have here a big molecule that actually has a hydrophilic end, and the rest of the body is hydrophobic. So a molecule like this can actually get along with something like water. It can actually get along with both. All right, we have here the hydrophilic end, which dissolves and works well with water, but then we have the hydrophobic end that doesn't get along with water. Molecules like this are incredibly useful. If we shift over here to this example, we have another image of the molecule here, but that one's kind of tough to see. We see here an oil droplet. Now, oil is very, very nonpolar, doesn't really get along with water. If you have oil mixed in with water, okay, and you want to try to remove it, well, you can't use water, right? So you have to use something that's going to get along with the water that it's in and get along with the oil. Stearate's a great example. You'll see that the nonpolar ends of stearate, the hydrophobic ends, are all mixing in and grabbing onto the oil droplet. And the hydrophilic ends, the polar ends, are all sticking out, and they're actually going to get along with and run with the water. All right. I think I used this example a long, long time ago when talking about detergents, how detergents work, right? When you wash your clothes, soaps, a lot of soaps work this way. You have oil and dirt and stains like that on your clothes. Most of them tend to fall in the category of being nonpolar. Just using water isn't really enough to get them out, especially if they've been in for a while. So using something like a molecule that does this, the nonpolar ends collect and surround the nonpolar dirt or oil, and the polar ends of the molecule actually agree with the water and wash away with the water, and your stains are then gone. Really neat idea that molecules can actually have both a hydrophobic and a hydrophilic end to them. Okay, so we can have colloids that exist this way. Okay, that kind of float around with the water. You have the hydrophilic end that mixes with the water, and you have the hydrophobic end that is trying to get away from water as much as possible. Okay, one last thing we need to worry about when it comes to colloids are how to remove them. Okay, how do you get rid of them? So sometimes particles must be removed. But these particles, even though they are sometimes large, they're not large enough, hence they are too small to be filtered. So we can't use something like filter paper to get rid of them. They're too small for that. Okay, so we need more creative ways. So particles, we got to make them big. We have to make them larger. Basically, we have to clump them together. Particles must, particles must be, oh, that looks ugly. I'll make that a different color. Okay, particles must be, that's not as ugly. Particles must be enlarged through what we call coagulation. Okay. Then we can filter. We can filter them out, or if they're really big, sometimes they'll just settle out on their own. To do this, we can heat them. Heating helps. You heat up a colloid, particles move more. That one, a little arrow here. Moving particles causes collisions. And then the particles, quote unquote, stick together. Okay. So that's one really simple way to separate out a colloid. Heat it up, particles stick together, and most of the time they stick together so much that their masses increase and then they just settle out, sink to the bottom. Okay. Try doing that to something like milk. It gets pretty disgusting looking, I suppose, but you can get a lot of those fat molecules to settle out and separate. It's kind of neat. One other thing you can do is you can add an electrolyte. So most soluble ionic compounds, those are electrolytes, right? They dissolve in water to form ions. So adding an electrolyte helps as well. Doing this removes any electrostatic repulsions. So molecules, quote unquote, stick. Hopefully you can see that. So sometimes colloid molecules, they repel each other, right? They either are charged the same or they're not charged at all, which gives them no reason to interact or bond together. So you dump in some electrolytes, they kind of surround the colloids and they provide positive charges and or negative charges, whatever's needed, they're there, and they cause a lot of attraction to happen between the colloids. They surround them. Also, again, kind of neat. And they allow them then to be attracted towards each other, right? If you have a whole bunch of electrolytes surrounding a colloid, it's got positive ends and negative ends, and it'll be attracted to another one that's surrounded with ions that have both positive and negative ends, and they all start to stick together, and same thing. They'll either settle out or they'll be big enough you can filter them. That's actually the reason why we have deltas, like in rivers. They form because of this process. As rivers run, they collect up a whole bunch of things. Of course, there's all sorts of solutes in natural bodies of water. But one of the things it picks up is something like clay. And so the river carries that clay all the way down, and then once it hits the ocean, right? You hit the ocean, now you have salt water. So that water then gets mixed up with tons of ions, electrolytes, from the salt water. And that actually causes the clay that was suspended to actually fall and settle out. And you get a river delta. Kind of neat. All right, that's pretty much all there is to know about colloids. It's very, very short, very small. Kind of just be familiar with their definition and be familiar with a little bit of how they work. Okay, know some of these processes, like know your definitions for hydrophilic and hydrophobic. One easy way to remember, hydrophobic, right? Phobic, phobia. Phobias means fear. That's the way I always got it, right? Hydrophobic, I always knew meant water fearing. And I knew water was polar, so I knew that that meant non-polar. Once you know that one, then hydrophilic's just the other way, right? Loves water. Be able to describe them, identify them, know what the Tyndall effect is, and then how to get them to settle out. These two ways. All right, make sure you guys spend this time studying, reviewing your concepts for Chapter 14. Be ready to go for your Chapter 14 quiz. And, of course, please continue to prepare for your final. Okay? You don't want to fall behind on that. All right, good luck.
Made with Doodlecast Pro.